Welcome to LIB Academy. In this video, I am going to take you through how to identify a chirality center, how to determine whether a given molecule, a given organic molecule is chiral or achiral. Chirality center or a chiral carbon is a carbon with different force substituents attached to it. So looking at this carbon here, it has hydrogen attached to it, fluorine attached to it, bromine, iodine. So it has 4 different groups attached to it. So this carbon is a chiral carbon, and therefore the molecule here is a chiral molecule. Looking at this carbon too, is it chiral or achiral? Well, we have bromine attached to it, hydrogen here, and then hydrogen here, and then fluorine here. So it has 4 groups attached to it, but they are not all different. We have hydrogen repeating, so this carbon here ceases to be a chiral carbon, and therefore it is achiral. Is this molecule chiral or achiral? Now, if we are given a molecule that has more than 1 carbon atom, we will be looking at a carbon with 4 different substituents and then a line of symmetry. If there is a chiral carbon in the molecule and the molecule has a line of symmetry, then it ceases to be chiral. While looking at this carbon here, we can redraw this to be CH3, okay, which H, C here with 2 hydrogens, and this carbon too with 2 hydrogens, and that carbon there with 3 hydrogens, a methyl group, 3 hydrogens. So let's look at this carbon. Is it chiral or achiral? Well, you could see that we have about 3 hydrogens attached to it. Then this carbon is not chiral. Here too, is this carbon chiral or achiral? We have a methyl group attached to it here, and then an ethyl group attached to it here. This is different from that, so they are different groups, but we have hydrogen here and hydrogen here repeating. So this carbon is not chiral. What about this carbon too? Well, since we have hydrogen repeating, then it is achiral. What about this carbon? It is also achiral. The carbon should have 4 different substituents. 4 different substituents before we can consider it to be a chiral carbon. So definitely, if you are given this molecule and you are asked whether it is chiral or achiral, you could see that there is a line of symmetry here, a line that divides the molecule into 2 parts. We have 2 carbon atoms at the right hand side and 2 carbon atoms at the left hand side. So this molecule is not chiral. The same thing, if you draw it this way, you could see a line of symmetry here. Identify the chiral centers in this molecule, the possible chiral centers in this molecule. Well, let's look at the carbon atoms one after the other. This carbon right here, atom here, is a methyl group. It has 3 hydrogens attached to it. Notice that. And this this one too is also a methyl group. It has 3 hydrogens attached to it. And this too has 2 hydrogens. One thing you can know that it has hidden hydrogen is that the carbon atom should have at least it should have 4 bonds. It should be bonded to 4 atoms. So now this one too also has a hidden hydrogen. So 1, 2, 3, 4 in all 4 bonds. So now, is this carbon here a chiral carbon? Definitely no. You could see about 3 hydrogens attached to it. We are looking at a carbon that has 4 different groups. So definitely this carbon is not chiral. Is this carbon chiral? You can see 2 hydrogens, so it is not chiral. This carbon too is not chiral. What about this carbon here? Well, this carbon right here is bonded to hydroxyl group, which is here, and hydrogen group, and a methyl group. And this too is an ethyl group. So a methyl group is different from an ethyl group. Here, the carbon is bonded to a methyl group, and here it is bonded to a carbon that is bonded to a methyl group. So this, the left hand side of the molecule here, is different from this. So since this carbon here is bonded to 4 different groups, then the molecule is chiral. Indicate whether this molecule is chiral or achiral. Sorry. Well, but don't forget that after identifying the chiral carbon, you should be also looking at the line of symmetry. We found this carbon here to be chiral, right? But there is no line of symmetry. There's no a line that will divide the molecule into 2 equal parts. If we divide the molecule into 2 equal parts from here, we have a methyl group here and an ethyl group here. So definitely ethyl group is not the same as methyl group. So this molecule is chiral. So is this molecule chiral or achiral? Well, we'll be looking at the chiral carbon. So we have a carbon here, which has 1, 2, 3 bond, means we still have a hidden hydrogen there. So we have a carbon bonded to a methyl group here and bonded to an iodine, bonded to a hydrogen, and bonded to a carbon with iodine substituent and a methyl group. So this side is different. So it means that this carbon right here is bonded to 4 different groups. So the carbon here is chiral, right? All right. So let's look at this carbon too. Is this carbon chiral? It has there is a hidden hydrogen here. So bonded to iodine, bonded to a methyl group, and then bonded to a carbon with iodine substituent and then methyl group. So this carbon atom here is chiral. Chiral. But is there a line of symmetry? Is there a line of symmetry? Yes. You could divide this molecule into 2 equal parts. This part we have iodine in on the solid wedge, the carbon with iodine on the solid wedge, and it also has a methyl group. This carbon right here will also have iodine on the solid wedge and then a methyl group and a hydrogen. So the right hand side here is equal to the left hand side here. Therefore, this molecule has about 2 chiral centers, but the molecule in total is achiral because of the line of symmetry. So notice that. Is this molecule chiral or achiral? Well, let's look at the carbon atoms in the molecule one after the other. This is a methyl group. This carbon has 3 hydrogens attached to it, hidden hydrogens, so it is not chiral. This carbon too, there would be hidden hydrogens here too, so it is not chiral. And this carbon, there will be a hydrogen here. So this carbon here has a methyl group, a hydrogen, and an ethyl group here, and then an ethyl group here. So looking at this carbon has hydrogen methyl group. This is an ethyl group, and this is an ethyl group. And the ethyl group ethyl group are the same, right? The carbon atom should have 4 different substituents or 4 different groups attached to it. So this makes the carbon atom here achiral because we have ethyl groups repeating. So this this molecule is achiral because it has achiral carbon, then it's definitely an achiral molecule. You could even see a line of symmetry here that will divide the molecule into 2 equal parts. Is this molecule chiral or achiral? Well, to determine whether the molecule is chiral or achiral, we examine the molecule to see whether it has chiral carbon, and if it has, then we look at a plane of symmetry, whether it has a plane of symmetry. So looking at this carbon here, it is a methyl group. It has 3 different hydrogens, so this carbon atom is not chiral. Here there is 2 hidden hydrogens here, so this carbon is not chiral because we have hydrogens repeating. Here too the same, so this carbon is not chiral. So look at this carbon, it has hydrogen, a methyl group, a bromine, and and a propyl group. A propyl group. So this carbon atom here is chiral. So there is no a line of symmetry, any line that will divide the molecule into equal parts. If we put a line of symmetry here, this one will be different from that. Here too the same, and then here too the same. This part of the molecule will be different from this. So this molecule is chiral, and the molecule has 1 chiral center. The next thing you need to know is the maximum number of stereoisomers. To determine the maximum number of stereoisomers, the formula to use is 2 to the power n, where n is the number of chiral centers in the molecule. So looking at this molecule, for instance, we have 1 chiral center, right? So the total or the maximum potential number of stereoisomers would be equal to 2 to the power n. And our n here is 1. It has 1 chiral center. So 1. It means our total stereoisomers, our maximum potential stereoisomers that we can get in this molecule is 2. So it's either R, S, or S, R. Now we'll look at the R and S configuration later. So what you need to know here is how to calculate the maximum number of stereoisomers of a given molecule if you know the number of chiral centers in the molecule. Is this molecule chiral or achiral? Or how many chiral centers can you see in this molecule? So straightforward, we start looking at the carbons that has 4 different groups attached to it. So we have a carbon here with 4 different groups, a carbon here attached to hydrogen, attached to a methyl group, attached to a hydroxyl group, and also attached to another substituent here. Definitely it has 4 different groups attached to it. So this carbon here is chiral. Well, this is not chiral because we have 2 hidden hydrogens here. Now let's look at this carbon. It has a long group here attached to it, that is 1, a hydrogen, that is 1, and then it also has a carbon attached to it here and a carbon attached to it here. But so how do we know that this side of the molecule that is attached to the carbon with 4 different groups, and that side of the molecule are the same or not the same? Well, we start looking at a plane of symmetry. So with here, you can divide this molecule into 2 equal parts, where this side we have an ethyl group, which is 2 carbon, and this side we also have ethyl group, which is 2 carbon. So it means this side of a molecule is the same as that side of the molecule. So this carbon ceases to be chiral, right? So we have only one chiral center in this molecule. So making the molecule a chiral molecule. What of about this? We start looking at the carbon atom with 4 different groups attached to it. From here, you can see that this carbon is chiral. I mean, here you have OH group, H group, methyl group, and another group attached to it. This carbon is chiral. This carbon is not chiral. This is not chiral. What about this carbon right here? Well, we have a carbon. This carbon is attached to a carbon here with a methyl group and another group. And this carbon here is attached to a carbon here with other group, right? With other groups aside. So definitely, if we are to imply the line of symmetry idea here, let's try dividing the molecule into 2. I mean, the other part of the molecule into 2. You will see that we have a carbon here with a substituent, but this carbon has no substituent, right? So definitely, this carbon here is different from this carbon. So they are different groups. So making this carbon here a chiral carbon. Another thing to know is we are looking at the carbon atom next to the carbon atom that is in consideration. We have this carbon here. It has no substituent, but we have this carbon here, which has a substituent. So definitely it is different from that carbon. So this carbon atom here is chiral because it has 4 different groups attached to it. So now let's look at this carbon. Yeah, is it chiral or achiral? There is a hidden hydrogen here. Well, this carbon has a methyl group here and a hydrogen attached to it. If we trace it to this side, it has a carbon with a substituent here. If you trace it to that side, it has a carbon with a straight substituent. This substituent here is different from this substituent. So making this carbon atom a chiral carbon. So chiral carbon number 3. So in all, this molecule has 3 chiral centers. Chiral centers. And the molecule is chiral. Sorry. Chiral. So let's look at the maximum number of stereoisomers that this molecule can have. So it's 2 to the power n. So 2 to the power n. N is the number of chiral centers. In this case, we have 3 chiral centers, 2 to the power 3, giving us 2 by 2 by 2. So 2 by 2, 4 by 2, 8. So 8 chiral, 8 stereoisomers possibly. So let's say it could be R, 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 R. It could be R, R, S. It could be R, S, R. It could be S, R, R. It could also be S, 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 R, S, R, S, S, R, S, S. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 possible stereoisomers. We will look at the RNS configuration in our next video. So this video is basically about identifying chiral centers and telling whether the molecule is chiral or achiral. So you can check the playlist on stereochemistry. So identify the chiral centers in this molecule. Bromine, bromine. Is this molecule chiral or achiral? Well, we are looking at the carbon atoms with different groups attached to it. So let's stand on this carbon here. There is a hydrogen here. It has a hydrogen, a bromine, and then a substituent here, and then a substituent here. But sometimes, once we see a plane of symmetry, then it means the molecule ceases to be a chiral molecule. Looking at this substituent here attached to the carbon here, this side is definitely the same as that side. So this carbon atom is not chiral, and this is not chiral too, because we have all of them on the dash wedges. So there is a plane of symmetry here that will divide the molecule into two equal parts. So this molecule is a chiral. So tell me, determine the number of chiral centers in this molecule. Bromine, OH group here, and then isopropyl group. So we will be looking at the carbon atom with 4 different groups. You can easily ignore this because you know that they have 2 hydrogen atoms attached to them. So this one, we have an OH group attached to it, a bromine group attached to it, and then this substituent, a carbon atom here with a carbon atom, with the next carbon atom having an isopropyl group, and a carbon atom here with the next carbon atom here having a next carbon. So which means that this side is different from this side, because looking at the first carbon attached to the carbon atom in consideration, it has a carbon with a substituent. Looking at this carbon, it has a carbon which has no substituent. So this side is different from that side. So this carbon atom here is chiral. So a chiral center number 1. So let's look at this carbon here. Is it chiral or achiral? Mind you, this isopropyl group is attached to the carbon atom here. We have another hydrogen atom here. So we have a carbon atom with an isopropyl group, a hydrogen, and here the carbon attached to it here has a carbon with OH group and bromine group, and the carbon attached to it here has a carbon with no substituent. So this side is different from that side. So this carbon here is a chiral center, which is chiral center number 2. So in all, this molecule is a chiral molecule, and the maximum potential number of stereoisomers that we can get here with 2 chiral centers equals 2 to the power 2, which is 4. Determine the number of chiral centers in this molecule and tell whether the molecule is chiral or achiral. Well, we are looking at the carbon atom with 4 different groups attached to it. There is hydrogen here. So this carbon atom has a methyl group, a bromine attached to it, a hydrogen, and another substituent at the side. So this is a chiral center. So let's name it number 1. This carbon, is it chiral? This carbon cannot be chiral because in all it has 4 bonds. Carbon double bonded to oxygen, the carbonyl carbon, and with a substituent here and a substituent here. So anytime you see a carbonyl carbon, know that it's generally not a chiral carbon. The bonds here are complete, right? But we have 2 bonds joining to oxygen, right? we should have the carbon with 4 different groups, but this carbon has 3 different groups. And we cannot add another group to it because it has a double bond. So it cannot be a chiral carbon generally. Now let's look at this carbon atom here. It has hydrogen here. So this carbon atom has a hydrogen atom and then a substituent here. And here too, it has a carbon bonded to a carbon bonded to a carbon. But do we have a line of symmetry here? Yes, we have a line of symmetry. In problems like this, what you should be looking at, a carbon that will have different substituent. I mean, let's say, okay, let's solve this one, then we do the other one we look at the another type of problem. So you could see there is a line of symmetry here, a line that will divide this side of the molecule into two to give us 2 carbon atoms here and 2 carbon atoms here at this side. So making this side of the molecule the same as that side of the molecule. So this carbon cannot be a chiral carbon because there is a line of symmetry that can divide the 2 carbon. That can divide the molecule, this side of the molecule into 2 parts. So in problems like this, step on the first carbon, you see no carbon with a substituent. Step on this carbon here, the next carbon has no substituent. The next carbon here has no substituent. Then you try looking for a line of symmetry, a symmetry. What about this molecule right here? If it has a methyl group here, an OH group here, carbonyl carbon, methyl group, and a bromine group. Let's look at the number of chiral carbons in this atom and determine whether this molecule is chiral or achiral. Well, this molecule here have, 1 carbon atom, so it is a chiral molecule. It has 1 chiral center, so it is a chiral molecule. So we know this carbon here has a methyl group, hydrogen, bromine, and another substituent here. So it is chiral, chiral center number 1. Carbonyl carbons are generally not chiral, so this is not a chiral center. And here we have carbon atom bonded to 4 different groups here. So this carbon atom has a substituent here and a hydrogen. So let's look at the other side of the carbon. So if we come here, we have a carbon. If we come here, we have a carbon. Let's go to the second one. Second one, we have a carbon. And second one here, we have a carbon with a methyl group, making this side of the molecule different from that side of the molecule. So now we are the second carbon. The second carbon here has a methyl group, and the second carbon here has no methyl group. So this is a chiral center. Let's name it chiral center 2. What about this carbon atom here? Definitely we know that this cannot be a chiral center, this cannot be a chiral center, this cannot be a chiral center because they have 2 hidden hydrogens, right? So in this case, we have a hidden hydrogen here. So this carbon atom here has a methyl group and a hydrogen attached to it. Now let's move to the next carbon. We have a carbon here, and here we have a carbon here with an hydroxyl substituent, making this side of the molecule different from this side. So this carbon atom here is chiral. So chiral center number 3. Okay, let's look at this too. We have a hydrogen here. This carbon atom has a hydroxyl group attached to it, a hydrogen attached to it. So now let's look at this side. It has a carbon here, and this side it has a carbon with a methyl group, making this side different from that side. So this is also a chiral center. So in all, this molecule has 1, 2, 3, 4 chiral centers. So 4 chiral centers, and the molecule is chiral. To look at the maximum potential stereoisomers is 2 to the power n, where n is the total number of chiral centers. In this case, we have 4. Then you evaluate it. Well, identify the chiral centers in this molecule. First of all, let's look at this molecule here. We are looking at a carbon atom with 4 different groups attached to it. This carbon atom here has a methyl group here and a methyl group here. Since we have methyl groups repeating, so the carbon atom here is not chiral. Let's look at this carbon atom. There is a hidden hydrogen here. This carbon atom has a bromine attached to it and has a carbon atom that has 2 methyl groups. And here too, it has a carbon atom that has, here we should have a chlorine here, that has a methyl group and a chlorine attached to it. Once again, the carbon next to a carbon atom in consideration has 2 methyl groups here at the right hand side. And the carbon next to the carbon atom in consideration to the left has a chlorine group, a chlorine attached to it and a methyl group attached to it, making this side of the molecule different from that side. So this is a chiral center. Let's name chiral center number 1. What about this carbon atom here? Is it chiral or achiral? Well, we have a hidden hydrogen here. We have a chlorine, we have a methyl group, and we have this substituent here, which is different from those substituents, making this carbon atom a chiral center. So chiral center number 2. So in all, this molecule has 2 chiral centers. And the molecule is chiral. Let's look at this. How many chiral centers do we have here in this molecule? Well, we are looking at the carbon atom with 4 different groups. Looking at this carbon atom here, it has a methyl group, an iodine, hydrogen, and a long substituent here. So this is a chiral center. So this can be a chiral carbon because it has 2 hidden hydrogens here, hydrogens repeating. So we forget this. What about this? We have a methyl group. There should be a hidden hydrogen here, a methyl group, a hydrogen, and a long chain here, and a cyclic chain, making this carbon atom chiral. So this is a chiral center. Let's name it number 2. Do we have, what about this? Is this carbon atom a chiral carbon? We have a hidden hydrogen here. Now this carbon here has a carbon attached to it here, a carbon attached to it here. So let's go to the second one, carbon, carbon, and they are coming together to meet at this carbon. This will tell you that there should be a line of symmetry. So in problems like this where you see carbons following each other, try to look for a line of symmetry. If there is a line of symmetry, then that carbon is definitely going to be a chiral. So you could see a line that can divide the molecule to come and pass through this carbon atom to give us 2 carbon atoms at this side and 2 carbon atoms at that side. So making this part of the molecule the same as this part of the molecule. So this carbon, since it has the same part of the molecule, two groups of the same molecule attached to it, it's easy to be a chiral carbon. So in this molecule, we have about 2 chiral centers. 2 chiral centers, one here and one here. So the molecule is chiral. Why are we not trying to find chiral centers with this carbon atom? Because you can see they have hidden hydrogen, hydrogens repeating, hydrogens repeating, hydrogens repeating, hydrogens repeating, hydrogens, 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 hydrogens. So now we are looking at the carbon atom with 4 different groups attached to it. Well, let's look at this molecule and determine the number of chiral centers it has. Well, we'll be looking at the carbon atom with 4 different groups. So this one here, this carbon atom has a methyl group, a hydrogen, a bromine, and a long substituent here. So it is a chiral center. Let's name it number 1. This one can be a chiral center. It has 2 hidden hydrogens. So let's look at this carbon here. It has a substituent here. It has a carbon here, and with the next carbon having a methyl group and a bromine group. It has a carbon here which has a methyl group. So this side is different from this side. It has a carbon here which has a carbon with hydroxyl group. So this side is different from that side and that side. Notice that we have hydrogen here and a hydrogen too. So this side of the molecule is not the same as this side, and it's not the same as this side. They are totally different. So this is a chiral center. Let's name it 2. Let's look at this carbon. Is it chiral or achiral? So this carbon has an OH group attached to it, a hydrogen attached to it. So let's look at this side. We have a carbon atom here. We have a carbon atom here. With a cyclic group attached to it. So looking at this carbon here, it branches here to a carbon and a carbon here. By looking at this carbon here, it goes straight to a carbon and then branches. It is the second carbon that joins this. It is the second carbon that joins this branches into 2 parts. But here it is the first carbon that joined the carbon center into, and it has 2 branches. So definitely this side is different from that side. So this carbon atom here is a chiral center. So let's name it 3. Now let's look at this carbon atom here. Is it chiral or achiral? There is a hydrogen here. A hydrogen here, and this carbon atom has a carbon that has an hydroxyl group. It is different. And let's look at this carbon. It has a carbon that branches into 2, and this carbon has a carbon that joins a carbon and then branches. So let's look at the first carbon joining the carbon atom in concentration. The first carbon joining the carbon atom in concentration here has 2 branches, right? But the first carbon joining the carbon center here has no branches, just straight. This telling us that this side of the molecule is different from this side of the molecule. So the center here is a chiral center. So let's name it 4. So let's look at this. We have a carbon atom here. There is a hidden hydrogen here. It has a methyl group here. The first carbon joining the atom in concentration has 2 branches. And the first carbon here joining the carbon atom here has 2 branches. So now we now have to consider which one has a substituent. So here 2 branches, 2 branches. Let's take one of the branch. Now we are here and here. So here we look at this, it goes straight, and we look at this, it goes straight with an isopropyl group. So this side has an isopropyl group, but this side here has no substituent, making this side of the molecule different from that side of the molecule. So this is a chiral center. So let's name it 5. So now the next thing we want to do is to look at this carbon atom here. This carbon atom here. Is it chiral or achiral? Before we continue with that, let's look at this carbon atom because it has 4 groups attached to it, 1, 2, 3, and a hidden hydrogen. So it has a hydrogen atom, and let's look at this side, carbon here with a methyl group, and let's look at this side, a carbon here with an isopropyl group, so which are different, and here a carbon here which branches to a carbon with a methyl group and branches to a straight carbon chain here. So this side of the molecule is different from that side and from that side. So this is a chiral center. So let's name it 6. So looking at this side too, it has an isopropyl group. There is a hidden hydrogen. Isopropyl group 1, hydrogen 2, and it has a carbon here that branches to 2 other carbons, right? By here, it has a carbon that joins to a straight carbon. So this side is totally different from that side of the molecule. So this is also a chiral center. Let's name it 7. Do we have other carbons that we can see whether they are chiral or achiral? Well, I think that is known because these carbon here, they all have 2 hydrogens attached to them. So just ignore them. So in this molecule, we have about 7 chiral centers. 7 chiral centers. And the molecule is a chiral molecule. To look at the maximum potential stereoisomers this carbon atom can have is 2 to the power 7. That is it for this video. Feel free to check my playlist on stereochemistry. The next video will be looking at the R and S configuration, phasor projections, and a whole lot of stuff. See you in my next video. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.